In this video, I want to discuss forces in circular motion. So, if you haven't reviewed the vector description of rotational motion recently, you really need to go back and watch those videos again before you take on forces in circular motion, because this sort of assumes that you've got that down pat. We'll do sort of a quick review here. So, imagine that we have motion here in a circle. We have some mass that's going around in this circular orbit. And so if I establish a coordinate system here that's in the center, here's plus x plus y, and then I can set up another coordinate system with unit vectors defined relative to plus x and plus y at each point where the object is. So I define a radial axis that points outward along the line from the center to where the object is, and then an axis that's tangent, which t hat, to the circle at the point where the object is. All right. And so I also want to, in this case, define a z-axis perpendicular to x and y, and I want it to be a right-handed coordinate system. So in this case, the positive z is out of the screen. And you can form a right-handed coordinate system if you point your index finger along the positive x and point your middle finger along positive y. If you stick out your thumb, then your thumb is going to point in the positive z direction, which in this case is out of the screen. And so I also then have a z-axis then out of the screen, which is perpendicular to the plane of rotation for my radial axis and tangential axis as well. So in this using these new unit vectors, that sort of radial and tangent to the circle at each point on the circle, I can then establish the relationships between my position and velocity that look like this. My radius is equal to some constant r, and then that points along the radial unit vector. My velocity then has a component which I call the tangential velocity that's always tangent to the circle. So while r is always positive, this is the magnitude, this is the component along the tangential axis. It can be positive or negative depending on whether it's going, in this case, counterclockwise or clockwise around the circle. But it's always tangent to the circle, while the radius is always radial. The acceleration vector, then, has a component that's tangential to the circle, as well as a tangent that's radial to the circle. Now, this component of the acceleration radial to the circle is often called, and I have to, the centripetal acceleration, which I might call A sub c. And I'll go back and forth between radial acceleration and centripetal acceleration, and they mean exactly the same thing. So you might wonder why I do that. I mean, why not choose to call it one thing and stick with it? And the reason is because there are people out there in books that call it, that use both terminology, and so you need to be familiar with both. It's just like when you learn a language. There may be 5 words that mean exactly the same thing. Does that mean you can get away with only learning one of them? No, you have to learn all 5 because you might encounter people that use all 5 and you have to know all 5 words. It's the same thing here. As you go through other physics, talk to other physicists or scientists, engineers, or other books, they may refer to this as either the radial acceleration or centripetal acceleration, and you need to be familiar with both terms. All right, and so we were able to relate these parameters to the parameters of rotational motion because the tangential velocity was equal to the angular velocity times the radius. The tangential acceleration was equal to the angular acceleration times the radius. And then the radial acceleration, or centripetal acceleration, was equal to the angular velocity negative, always negative, angular velocity squared times the radius. Here, omega or alpha can be positive or negative, just like the tangential component of the velocity or acceleration can be positive or negative. Here, the omega squared is always positive and r is always positive, and the centripetal acceleration is negative when my r hat points outward from the circle. The radius, the radial unit vector points outward. And another way to write this, then substituting this expression into here, you can also write this as negative v squared over r, where v is the tangential velocity. All right, so there's sort of our, I guess, 6-minute review of circular motion. So what I want to look at here, so I want to look at forces in circular motion to see how forces lead to accelerations. So how do forces lead to these accelerations within circular motion? To do that, I mean, the answer to that is simply you apply Newton's second law. And so to be able to do that, let's look at an example. I'm going to look at a toy that goes along a track with a hoop. So this is a toy car moving along this track, and it just rests on the track. We're going to assume it's frictionless, but it is not attached to the track in any way. It is simply rolling along the track. And so if I know, and you probably have too seen this, if the car is going fast enough, it can go all the way around this loop without falling off. So let's look at the car when it's exactly at the sideways on the loop. We're going to look at the car when it is on the top of the loop, and then sort of down here when it is finishing the loop, and it's going around the loop counterclockwise, and then of course later on it's still moving. All right, so let's look this at position A, position B, and position C, and I want to apply forces at each point of the motion. So first, all right, so let's look at point A. So I'm going to choose an object, and which object of course is my car, and I want to find all the forces on that object. So the forces, this is at A. So what are the forces? The forces are gravity. I'll call that F sub g. So there's also the normal force of the track on the car, so I'll call that N, because it's in contact here. Is there anything else in contact with the car? And the answer is no. We've assumed it's frictionless, so the contact force between the track and the car only has a normal component. So these are the only forces we have. All right, so now we need to do a free body diagram. And so I know that the force due to gravity is towards the center of the Earth. And the normal force is perpendicular to the surface of contact between the agent and the object in the direction from the agent to the object. The agent is the track, the object is the car, so it's pointing in that direction. What about my coordinate system? Okay, so I want to work in this circular coordinate system. So at this point, there's the radius vector from the center to the point where my car is. So at this point on the track, there's going to be, by radial axis, the unit vector that points radially to the circle is in that direction, horizontal to the ground, if it's exactly at sort of 3 o'clock here on my hoop. And then the tangential axis at this point on the track points straight up. So if I establish that axis plus r plus t for my free body diagram, I now want to sum my forces, and when I sum my forces, I want to find the components of my forces along these radial and tangential unit vectors. And then I can use my circular motion notation to be able to solve F equals ma. All right, so let's do that. So let's vector sum my forces. There's the force due to gravity. So it has 0 component on the r-axis, and it has its entire magnitude. Force due to gravity is mass of the car times g along the tangential axis, and given that the tangential axis is up, that means the component of the gravitational force is down. And there is no component of forces in and out of the screen, so there's no component along the z-axis. I'm just going to leave that off for now. And so then I have the normal force, which has the entirety of its magnitude radially, and from the diagram, it is also pointing on the negative r-axis, and it has 0 component tangential to the circle. So I'm going to sum, just like before, I sum my forces, and that is equal to the mass of the car times the acceleration. But now this is where this notation and working in this coordinate system pays off, because I can now identify this component along the radial axis to be my radial or centripetal acceleration. And this component of my acceleration along the tangential axis is the tangential acceleration. So now, when I establish the relationships between my components, I can identify, so I can identify that the normal force then, the opposite of the normal force, is equal to the mass times the radial acceleration, which is the mass times negative omega squared r, or negative m tangential velocity equals r. So now I can relate, say, my force, and my normal force, equal to, or relate it to my tangential velocity in this way. And I can only really do that if I sum my forces along components that are radially and tangential to the circle at that point. So my second expression gives me that negative mg is equal to m times the tangential acceleration, or that my tangential acceleration at this moment is negative g. So that's an example of just F equals ma for something moving in a circle. But we're going to do B and C because we want to look at this in different examples. Okay, so let's look at B now. So the point is, at each different point in the circle, of course, the radial unit vector and the tangential unit vector are going to be pointing in different directions relative to the lab axis, x and y, and relative to the ground. And so you have to take that into account for each point in space. So okay, so this is this radial and tangential unit vectors at point B. So let's look now then at point B. What are the forces? The same forces. Gravity and the normal. The f of g and the normal. That hasn't changed. We'll draw a little box, gravity, and the only thing in contact with it is the track. We're ignoring air resistance, no friction, etc. So now what changes then is when we go to the free body diagram. So now we have, again, our force due to gravity, which is down. But at the top of the loop, the normal force is always also pointing down. because it points from perpendicular to the surfaces of contact from the agent to the object, from the track to the car, which is down. So now, when we sum these vector forces, oh well, of course, let's get our coordinate system. So in our radial tangential coordinate system, which is here, we have positive r is up, and positive t is to the left at point B. So now we can sum the forces along the components along this coordinate system. The force due to gravity, I guess, get too much red here. The force due to gravity then for point B has it's the entirety of its magnitude along the radial axis, and it's then the negative radial axis, and then nothing along the tangential axis. The normal force has the entirety of its magnitude along the radial axis, and from the free body diagram it is also negative, and nothing along the tangential axis. So I vector sum the forces equal to the mass of the object times its acceleration, and this is now the mass times the radial acceleration plus the mass times the centripetal acceleration, t. So in this case, what have we learned? Well, we've learned that the tangential acceleration is equal to 0 at point B. And also then that, move over here, that we have negative n minus mg is equal to mass times the radial acceleration, or the centripetal acceleration, which of course is equal to m negative omega squared r, and maybe that's what we want, or n plus mass mg, force due to gravity, is equal to m times tangential velocity squared over r. Maybe you want omega or the velocity, it depends on the problem. But this now is the relationship between the parameters. At the top, everything is along the radial axis, where at point A, the force due to gravity was giving us a centripetal acceleration, a tangential acceleration, while it was only the normal force which was providing the centripetal acceleration. And in point B, both forces are providing the centripetal acceleration, and the tangential acceleration is 0. All right, so now let's do point C, which mixes things up a little bit. So this is now here going down at some angle relative to the horizontal, which we will call theta. So at this point, we have r, which is radial to the circle, and tangential, which is tangential to the circle, but everywhere so that our coordinate system is right-handed, meaning I want my index finger pointing along the r direction, my index finger along the r direction, and my middle finger along the tangential direction, and my thumb points out of the board, which I define to be my positive z-axis, which in this configuration it does. All right, and so now I have to be a little careful when I do my projections. Okay, so let's look now at point C. What are the forces? The same ones. We have the same forces that we had before. Okay, but where are they now? So the force due to gravity is still straight down, but the normal force acts perpendicular to the surface from the agent to the object, so it's pointing off at an angle. this way. Okay, so to figure out where that is exactly, I want to put in sort of my two sets of perpendicular axis, one which is parallel and perpendicular to the ground, and then the second one is sort of parallel and perpendicular to the surface. Okay, and so from the picture before, I know that this angle is theta, and so that translates to this angle here. Once I know that that angle is theta, that tells me this angle is theta. Every alternating angle is theta. And so given those thetas, I can now compute the components along the various axes. But where are those axes exactly? Given the system, how the object is rotating, there's the radial axis, and here's the tangential. On my free body diagram, that makes this direction the positive radial axis, and that direction the positive tangential axis. Now that I have my radial and tangential axis, I can sum the forces along these components. All right, so first I have the force, well, we can do the force due to gravity. Okay, so I need to find the components. So to do that, I draw my lines from the tip of my vector so that they make perpendicular with the axes. If the axes that where I want to find the components, if this angle is theta here, that means that angle is theta. And what I want to find then is I want to find the component along the positive, well, I want to find the component along the radial axis. That's the length of this line segment. So from trigonometry, the length of that line segment is the magnitude of my vector, which is right here. That's mg times sine theta, because this is theta. All right. So the magnitude, the length of that line is the hypotenuse, which is the magnitude of the vector, times sine theta. So that's mg sine theta r hat. Then I look on my coordinate system to see whether that's positive and negative, and I can see it's along the positive r-axis. All right. So next, I want to find the component along the tangential axis, which is here. And then I can just use trigonometry to find the length of that line. The length of that line is the length of the hypotenuse, which is the magnitude of the force, times cos theta, because this is theta, and that length of that triangle is adjacent to the angle. So that gives me mg cos theta as that component. It's along the tangential axis, and looking at my coordinate system, it's in the positive tangential direction. Okay, so then the next I want is the normal force, and it's entirely along the radial direction. And I find that looking at my coordinate system, it's on the negative radial direction, and it has no component tangential. So the sum of these forces, it's the mass of the object times the acceleration, and in circular motion, the mass of the object times the radial acceleration plus the mass of the object times the tangential component, tangential acceleration. So what sort of relationships does this give me? Well, it says that mg, well, I'm going to do I can set up my relationships from my components, which tell me that mg sine theta, sorry, I'm going to do cosine first, do the tangential. mg cos theta is equal to the mass times the tangential acceleration. So I do again have a tangential acceleration, and this is equal to g. The magnitude of it is g cos theta, and which means it's positive, which means it's speeding up at this point. Last time we had a tangential acceleration, it was negative g, which means it was slowing down. And of course that makes perfect sense. At this point it's going to be slowing down as it goes up the loop, and at this point it's going to be speeding up as it goes down the loop. So again, I'm sort of checking, right? I'm sort of moving into the checking stage of my problem solving just to make sure everything makes sense and is consistent. Looking in the radial direction, I have mg sine theta minus n is equal to mass times my centripetal acceleration. I'm going to use centripetal this time. It's the same as radial. And so that gives me mg sine theta minus n is equal to m omega squared r, negative omega squared r, or negative mv squared v tangential over r, depending on which is most useful. And so I might turn this around, and I might show that n minus mg sine theta is equal to m vt squared over r. So this now gives me my relationships between my parameters. Okay, and so here we can see how this works with forces in circular motion. In this case, because we went through all this work to establish these relationships between our kinematic rotational motion parameters, we want to work in a coordinate system where my forces are meaningfully related to these components. And that's done if we define our coordinate system at each instant radially and tangential to the circular motion. I want to end this with a very classic question, which is, what is the minimum speed? Let's go back up to the picture. What is the minimum speed such that the car makes it around the hoop? You know, if the velocity is too slow, it won't, in fact, make it up. It'll go up so far and then fall back down. And then you can, if it goes faster, it can make all the way up to the top, but if it doesn't have enough speed, then it just falls. So what is the minimum speed that it makes it all the way around the loop? All right. This is a classic problem. So I'll put it here. What is the minimum speed that the car makes it around the loop? This is identical to, say, if I had a mass on a string that's flexible and you spin it around in a circle, what is the minimum speed of the mass at the top so that the string does not go slack and the mass falls? Another one is the bucket of water. So imagine I have a bucket of water. And I'm going to swing this bucket of water around my head. And so what is the minimum speed I need to swing this bucket of water so that the water doesn't crash down and I get soaked? These are all exactly the same problem. Okay, so that is essentially the force analysis that we had before, which was at point B, which was here. And at this point, we found that the normal force of the track on the car, or the string on the ball, or the bucket on the water plus the force due to gravity on the object is equal to the object's mass times its tangential velocity squared divided by the radius of the circle. So mass and gravity are constant as well as the mass and the radius. So the two things that change is the velocity as well as the normal force. So as the velocity gets larger, when it reaches the top, the normal force is larger. And as the velocity decreases, the speed decreases, the normal force gets smaller and smaller. Eventually, the normal force goes to zero. And what does that correspond to? Well, that corresponds to, of course, the car leaving the track, or the tension going to zero means the string goes slack, or the normal force going to zero means the water is no longer in contact with the bottom of the bucket, meaning it falls out. So the minimum speed such that the car makes it around the track is the same as saying the normal force at the top of the track goes to zero. Well, in that limit, then, we simply have mg is equal to mass tangential velocity squared over r. Masses cancel, and the tangential velocity is equal to the square root of the acceleration due to gravity times the radius of the circular motion. And this is now the minimum velocity that these objects make it around in a circle without the catastrophic occurring.